We are going to start now the next lecture of chapter 6, class 11th mathematics. So in this lecture we will study about the logarithm and its properties, and these results will be useful in solving the inequalities related to the exponential functions and the problems related to logarithms that we will see in our next lecture. The first definition we have over here, it is logarithm. So we are saying the logarithm of any positive number, this thing is important over here, logarithm of any positive number whose base is a number greater than 0. So the condition on the base we have, it is always greater than 0, different from 1. This is another condition on the base. Is the index or the power to which the base must be raised in order to obtain the given number. So we are saying that if a raised to the power x is equal to b, where we are saying a is greater than 0 and a is not equal to 1, then the x is called logarithm of b to the base a. We are saying this expression we can also write it in the form that log b to the base a is equal to x, and we will have b is greater than 0. So what we obtain from this is that log b to the base a, that is equal to x. This implies us, and this is implied by that a raised to the power x is equal to b. Both these statements, these are equivalent, and the conditions we have over here, it is a is greater than 0, a is not equal to 1. This is the a, we are saying a is the base over here. This a, we are saying a is called the base of the logarithm, and b is greater than 0. So if we take a is equal to 10, we write it like log of b. If it is log of b, it means the base we have over here, it is 10, and if it is base e, we write it in the form this, corresponding to the base e is equal to e, then we write this. So this is the notation for this, is called natural logarithm, and this is the logarithm to the base 10, and the numerical value of this e, we are saying this number e, we are saying the numerical value, it is 2.7182. This is the numerical value of this number e. This number e we will study when we will talk about the sequences and series. So this is basically a limit of the series that we will study over there, but right now you can see it as just a number 2.7182, and the number, if we are calculating, it is log e to the base 10, it is equal to 0.4343. This number, it is called Napier's constant. This number is called Napier's constant, and we are saying that natural log of b, that is equal to 2.303 log b to the base 10. Why we are getting this answer? We are saying that log b, we are talking about the natural base over here, that is equal to log base 10b into log of 10 to the base e. This is equal to 1 by log e to the base 10 into log of b to the base 10, and the value of this term 1 over this term, we are saying it is equal to 2.303. So we have this result that natural log of b, if we have to convert it to the log to the base 10, we have to multiply it with this number e over here. We are multiplying basically it with the number 2.303. These are the values we are saying that you should remember. These are the direct values we have First is we are talking about the log of the number 2 to the base 10. The value we have it is 0.3010. Next is log 3 to the base 10. It is 0.4771. And if we are calculating the natural log, we are talking about natural log of 2, we have to multiply this with 2.303. The answer we have it is 0.693, and natural log of 10, that is 2.303. Now next we are going to discuss the properties of the logarithm. The first property we are saying, it is called the fundamental logarithmic identity. So we are writing, if a number is given to us in the form, we are saying it is, we are talking about the equation, it is a raised to the power log a b, that is equal to b. Why we are getting this result? The definition we have, it is a raised to the power x is equal to b. This statement is equivalent to x is equal to log b to the base a. So if we write this in this form, we are saying the statement log a raised to the power log b to the base a is equal to b. This term, it is equivalent to the condition that log base a b, that is equal to log b to the base a, and this is what we are saying over here. So we look at this definition over here, this condition over here. If we apply this condition over here, we get that this result is true. So this identity we are saying that a raised to the power log b to the base is equal to b. This is called fundamental logarithmic identity. And the conditions over here, it is a is greater than 0, a is not equal to 1, and b is greater than 0. These three conditions, these are very important. You should not miss these conditions. Next is logarithmic function we are talking about. So we are saying a function fx which is equal to log x to the base a. Again, the condition on this base we have two conditions, that a is greater than 0 and a is not equal to 1. Then this function is called logarithmic function. The domain of this function, it is 0 to infinity. The values the x can take, x belongs to 0 to infinity, and the range of this function, it is all real numbers. The next property we have is for a raised to the power x greater than 0 for all x belonging to R. We are saying the condition on a we have it is, we are talking about that a is greater than 0. We are talking about the condition on a, it belongs to 0 to 1 union 1 to infinity. If a belongs to, the first condition we are talking about, when a belongs to the interval 1 to infinity, then we are saying that the function a raised to the power x is monotonically increasing. Monotonically increasing means that if x1 is less than x2, this implies us a raised to the power x1 is less than a raised to the power x2. So these examples are given over here. In this first example, we are saying that 3 is greater than 2.5. So this implies us that 5 raised to the power 3 is greater than 5 raised to the power 2.5. Similarly, 3 raised to the power 222 is greater than 3 raised to the power 111. Now second case we are saying, this is the first case we have considered when a belongs to this interval. Second case we are considering is when a belongs to the interval 0 to 1. We are saying a belongs to the interval 0 to 1. In this case we are saying a raised to the power x is monotonically decreasing. Monotonically decreasing means that if x1 is less than x2, this implies us a raised to the power x1 is greater than a raised to the power x2. So in this case we are saying, the first example we are saying it is, this number, it is 2.5. We are saying 2.7 is greater than 2.5. So this implies us, now we are the base we are taking over here, it is 1 by 5, and 1 by 5 is clearly less than 1. So we are saying that 1 by 5 raised to the power 2.7 is less than 1 by 5 raised to the power 2.5. So, we are saying that this inequality is reversed in this case, but this inequality will remain, the sign of this inequality, it will remain same if A is greater than 1. Next properties we have is, if A is greater than 1, then A raised to the power minus infinity is equal to 0, and if A belongs to the interval 0 to 1, then A raised to the power infinity is 0. So, what we obtain from these cases is, we are saying that log 0 to the base A is minus infinity and log 0 to the base is plus infinity. It depends upon if the value of A is greater than 1, and this will be the case if the value of A lies between 0 and 1. So, these are the next properties related to, we can say, exponential function or the logarithmic functions. Next we have is log b to the base A, it tends to infinity if A is greater than 1 and b tends to infinity, and log b to the base A, it tends to minus infinity if A belongs to the interval 0 to 1 and b tends to infinity. So, again for these two cases, when A is greater than 1 and A is less than 1, we have these two conditions. Next question we have is, we have to calculate the value of log 27 to the base 9. So, suppose we are saying that its value is x, we are saying x is equal to log 27 to the base 9. So, this thing implies us that 9 raised to the power x is equal to 27, and this is equal to 3 raised to the power 3, 27 we can write, and this 9 raised to the power x we can write 3 raised to the power 2x. So, if we compare the powers over here, it is 2x and 3. So, this implies us we are talking about 2x is equal to 3. So, we obtain x is equal to 3 by 2. The answer we obtain is x is equal to 3 by 2. Next question we have is log of 324 and the base we have it is 3 root 2. So, again if we consider this value is equal to x, so this implies us 3 root 2 raised to the power x, that is equal to 3 to 4, and if we factorize 3 to 4, we obtain the factors it will have. We are saying it is 2, then 6 and then 2, and it is 2, 8, 1, and we are getting it is 2 raised to the power 2 into 3 raised to the power 4. So, this implies us that 3 root 2 raised to the power x, that is equal to, we want to write this term as 3 root 2 to the power, it is 4. You can write this term, we are saying it is 2 raised to the power 2 into 3 raised to the power 4, we can write it is 3 root 2 raised to the power 4. So, by comparing the powers over here, if we compare the powers over here, this implies us that the value of x we have it is equal to 4. The value of x we have it is 4. Next is log of 27 root 3 and the base we have it is 1 by 9. Again we suppose it equal to x. So, we are solving over here 1 by 9 raised to the power x is equal to 27 root 3. This term we can write it is 1 by 3 raised to the power 2x, that is equal to, if we write this term it is 3 raised to the power 3 into 3 raised to the power 1 by 2. So, what we are getting from this is 3 raised to the power minus 2x, that is equal to 3 raised to the power 7 by 2. Look at these powers over here, it is minus 2x is equal to 7 by 2. So, the value of x we have that is equal to minus 7 by 4. So, we are saying that the value of x we have it is minus 7 by 4. Next is log of 5 plus 2 root 6 into 5 minus 2 root 6. Suppose it is equal to x. So we obtain this value. We are saying this implies us that 5 plus 2 root 6 raised to the power x is equal to 5 minus 2 root 6. Now we want to find the power over here. So we are saying that if we calculate the value of 5 plus 2 root 6 into 5 minus 2 root 6 divided by 5 minus 2 root 6, this value will be equal to 5 minus, it is 25 minus 24 over 5 minus 2 root 6, that is equal to 1 by 5 minus 2 root 6. So we are saying that this value 5 plus 2 root 6, this is equal to 1 by 5 minus 2 root 6. So in place of this equation, for this equation we are getting that 1 by 5 minus 2 root 6 raised to the power x is equal to 1 by 5 minus 2 root 6 raised to the power minus 1. So this implies us that the value of x we have, it is equal to minus 1. This is the value of x that we have in this case. Next question we have is to calculate the value of log of 0.008 to the base 0.2. So again, if we consider this value is equal to x, so we obtain, we are solving the equation, this is 0.2 raised to the power x is equal to 0.008. This implies us 0.2 raised to the power x is equal to 0.2 raised to the power 3, and this implies us x is equal to 3. Similarly, the next question we have, it is 2 raised to the power 2 log base 4 5. So suppose we are saying this value is equal to x. So we are writing it is equal to 2 raised to the power 2 whole raised to the power log 5 to the base 4. This is equal to 4 raised to the power log 5 to the base 4. And we have seen the formula that a raised to the power log a to the base b to the base a is greater than 0, a is not equal to 1. In this case we are saying this is equal to the value b. So we are saying this is equal to 5. This formula we have already studied. So we are saying the value of x in this case, it is equal to, we have 0.4 raised to the power minus log base is 2.5 and the number we have, it is 1 by 3 plus 1 by 3 square and so on. Clearly this term, look at this term over here, it is a GP. The sum of this GP will be, the first term we have, it is 1 by 3, the common ratio we have, it is 1 by 3. So the answer we obtain, it is equal to 1 by 3 over 2 by 3, that is equal to 1 by 2. So this problem becomes 0.4 we can write it is 4 by 10 raised to the power minus log base we have, it is 2.5 and the number we have, it is 1 by 2, and this is equal to 2 by 5 raised to the power minus log 2.5 we can write it is 5 by 2, the number we have, it is 1 by 2. So this is equal to, this negative sign is there in the power, so these terms will be reversed. So we will get it is 5 by 2 raised to the power log of 5 by 2, the number we have, it is 1 by 2, and we have studied the property in our previous slide that this number, it is a raised to the power log of b to the base a, the value we have, it is equal to 1 by 2, the value we have, it is equal to 1 by 2. So the answer in this case we obtain, it is 1 by 2. In this second question, the problem we have, it is, I am discussing the problem over here, it is 0.05 raised to the power log square root 20 and the number we have over here, it is 0.3 bar. Now first thing is we know that this 0.3 bar that we can write it is equal to 3 by 9 is equal to 1 by 3. If you look at this number, it is 0.05, we can write it is 5 by 100, that is equal to 1 by 20. So, this complete problem we can write it in the form 1 by 20 raised to the power log, base we have it is square root of 20 and the number we have over here it is 1 by 3. So, this is equal to 1 by 20, then it is log 20 raised to the power 1 by 2 and 3 raised to the power minus 1. We can write this is equal to 1 by 20 raised to the power, this minus 1 is there, it will come out. This 1 by 2 is there, we can write it is into 1 by 2 log base 20 and this number we have it is 3. Now, look at this term over here, it is 1 by 20 raised to the power minus 1, that will become 20. So, this is equal to 20 raised to the power 2 log base 23. This term we can write it is 20 raised to the power log base 29. The number we have 9 and the base we have it is 20. So, again using this result the answer we obtain it is equal to 9. So, we are saying the value of this term it is equal to 9 in this case. Question we have is, it is log of cot 30 degree and the base we have it is tan 45 degrees. This is the value of A, we have it is tan 45 and the value of tan 45 we know it is equal to 1, and as base cannot be equal to 1, the condition for the log we have it is that the base cannot be equal to 1. So, we are saying that this value is not defined because the function log it is not defined for A is equal to 1. Next is log of base we have it is secant square 60 minus tan square 60, the secant square 60 minus tan square 60. So, by identity again we have this base is equal to 1. So, in this case also this function or this value is not, log is not defined. Similarly, in the next case we have the base is sin square 30 plus cos square 30 and this value is again 1 and it is not defined, and last it is log base 31. We are saying the next question we have it is log 1 to the base 30 and we know that if we have the value 1 over here the answer is always equal to 0, because suppose we are saying x is equal to log 1 to the base 30. So, we are solving the equation that 30 raised to the power x is 1 and this implies us x is equal to 0. Next we have the definition of characteristic and mantissa. So, we are saying that the integral part of the logarithm it is called the characteristic and the fractional part is called the mantissa, the decimal part is called the mantissa. So, if we are talking about the log of the number, say we are saying log of 564, the answer we have it is 2.751279, then this 2 over here we are saying this is equal to 2 plus 0.751279, this 2 is called the characteristic and this fractional part we have it is called the mantissa. Similarly, if we are talking about the log of the number, say 0.00895, the answer we have it is minus 2.048179. So, we are writing this is equal to minus 2 minus 0.481769. If we are talking about the fractional part cannot be negative. We are saying fractional part cannot be negative. So we are writing it in the form, this is equal to minus 3 plus 1 minus 0.0481769. So this is equal to minus 3 plus 0.951823. So we are saying the characteristic in this case it is minus 3 and the mantissa in this case it is this term. So we are saying that the mantissa is never negative, and this number we write in short form, we write it in the form 3 bar. This 3 bar means this is the characteristic, and the mantissa we write it is 9518231. So this number when we are writing, it does not mean that it is minus 3.95. This is not minus 3.95, it is actually the number minus 2.048176.9. So this is the notation we have to write these kind of number. So the next property we have is, if n is, any number n is there and it is greater than 1, then the characteristic of log n will be 1 less than the number of digits in the integral part of n. So suppose we are talking about the number n we are considering, it is 235.68, and we are saying that the log of n will be 2.3723227. So the characteristic over here it is 2. Why it is 2? Because the number of digits in the integral part of n it is 3. So the characteristic we have for n it is equal to log n, we are saying it is equal to 3 minus 1 is equal to 2. Next we are saying, if n is between 0 and 1, that is n is less than 1, then the characteristic of n is negative and numerically it is greater than the number of zeros immediately after the decimal part in n. So suppose we are talking about the value log of 0.0000279. The answer we will have, it is equal to 5 bar, the answer in this case it will be 5 bar 0.4456042. So we are saying there are 4 zeros immediately after the decimal. So the number of, when we are talking about the numerical value of this term, the numerical value of this term we are saying it is basically 4 plus 1 is equal to 5. That is, it is 1 greater than the number of zeros immediately after the decimal part in n. Next is, if the characteristic of log n is n, then the number of digits in n is n plus 1. This thing is clear from our previous case. And if the characteristic of log n is minus n, then there exists n minus 1 number of zeros after the decimal part of n. So these are just the converse results corresponding to our first two results. Now the problems based upon this we have, it is, if log of 2, the value of log 2 is given to be 0.301, clearly this is a 1 digit in this number 2. So the characteristic we have over here it is 0, and if log 3 is equal to 0.477, you should remember both these values because these are the standard results that we have. Now we have to find the number of digits in 6 raised to the power 20. So suppose we are saying that 6 raised to the power 20, we are writing it is the number p, we are writing in this form, this is equal to 2 into 3 raised to the power 20. So if we take log over here, we are having log of p is equal to 20 into log 2 into 3. This is equal to 20 into log 2 plus log 3. If we add both these values, the answer we obtain, this is equal to 20 into 0.778, On multiplying these values, we obtain it is 15.560. So we are saying the number we have over here, the characteristic we have over here, it is 15. So the number of digits in P, that will be 15 plus 1 is equal to 16, and this is what we have to find the number of digits in 6 raised to the power 20, it is 16. Next is find the number of zeros between the decimal point and the first significant digit of 0.036 raised to the power 16. So again the values of log 2 and log 3, these are given to us. So suppose again we are writing this value is equal to P. If we take log, we will have log of P is equal to 16 log of 0.036. This is equal to 16 log of 36 by 1000. This is equal to 16 log of 2 raised to the power 2 plus log of 3 raised to the power 2 minus log of 10 raised to the power 3. We are using the result that log of A B by C, that is equal to log A plus log B minus log C, and this 36 we are writing, it is equal to 4 into 9, that is equal to 2 raised to the power 2 into 3 raised to the power 2. So the answer we obtain, it is 16 into 2 log 2 plus 2 log 3 minus 3 log 10. The value of log 2 we have, it is 0.301, log 3 we have it is 0.477, and log 10 we know it is equal to 1. So if we substitute these values, the answer we obtain, it is equal to 16 into 1.556 minus 3, and on solving this we get the final answer in the form this is equal to minus 24 plus 0.896. So this minus 24 is the characteristic and 0.896 is the mantissa. So we are saying the number of zeros we have, that is equal to the characteristic over here, we are saying the numerical part, it is 24. So it is 24 minus 1, that is equal to 23. So we are saying that the number of zeros between decimal point and first significant digit of this number, it is 23. Now we have listed some principal properties of logarithm. These properties we have already studied when we were discussing the logarithmic function in our chapter related to relations and functions. So the first property we are saying, it is log of mn to the base a. We are saying that is equal to log of m to the base a plus log of n to the base a. So this result, it can be generalized for n different values. We are saying that if it is x1, x2, x3, so on up to xn, then we are writing it is log of x1, log of x2, log of x3, log of xn, and the base we have over here, it is a, same in all these cases. And in the product notation, we are writing it is product of I is equal to 1 to n xi. What this thing means, it is x1 into x2 into x3, so on up to xn. Summation notation is in this form. We are saying I is equal to 1 to n xi. This thing means x1 plus x2, so on up to plus xn. So this is the notation for sum and this is the notation for product. So we are saying that if we have n different terms, product of n different numbers x1, x2, x3, so on up to xn, then we are saying it is equal to sum of log of xi. Then xi means, what this value means, it is log x1 to the base a plus log x2 to the base a, so on up to log xn to the base a. Next result we have is log to the base a m by n, that is equal to log to the base a m minus log to the base a n. So sometimes the students confuse this result with this, that they write log of a of m minus n, that is equal to log of m by log of n, but this thing is wrong. There is no result in this form. The result is, if we have division of two numbers m by m and n, we are taking log over here, it is log of m minus log of n. Next is log of m to the power alpha, and the base we have it is a. So we are saying this power, it is, we can write it is alpha log m to the base a. We can write this term in this form. So it is when m has the power alpha. Next we have, if this base we are saying it is having the power beta, we are talking about the term that it is log of m, the base we have it is alpha raised to the power beta, the answer we have it is 1 by beta log m to the base a. And last formula we have it is change of base. We are saying in this first term the base we have it is b, the base we have over here it is b. If we want to change this base to a, we are using the formula, it is log m to the base a divided by log b to the base a. So you must remember these formulas, these are very important, not just for the inequalities part. In derivatives we will use this formula, and in general also these formulas, these are very important. So you must remember all these formulas. Now the next results we have is, the first result we have over here, it is this result, it is a raised to the power log x to the base b. We are saying that is equal to x raised to the power log a to the base b, where b is not equal to 1 and a, b and x, these are positive numbers. So this result we have already seen in our previous slides. Next result we have is that a raised to the power log x to the base a, we will have this is equal to x. We can obtain this result by using this previous result we have. So we can write this value is equal to, we are saying this value will be equal to x raised to the power log a base a, and the value of this term will be equal to 1. So the answer we obtain it is equal to x. Next is log to the base a raised to the power kx. We have seen that this is equal to 1 by k log of ax. This result we have already seen in our previous slide. The next result we are saying it is log ax raised to the power 2k, that is equal to 2k log a mod x. So what we are saying over here, that if the power over here it is even power, then this term we will have mod x over here. Why we are writing in this form? It will be more clear to you with this example. We are saying that log to the base a x square, this will be equal to 2 log a mod x. So we are saying that log to the base a x square is not equal to 2 log a x. The reason being, the domain for this function it is r minus 0, and the domain of this function it is 0 to infinity. So the domain of both these functions, these are different, so they cannot be, we cannot equate both these values. So we are saying if we have the formula in this form, then the domains will be equal and this formula will be valid. So this is, we are saying the power we have basically over here it is even power, that is why we should have mod x over here. Similarly, in the next case we are saying that if the power of this base is a raised to the power 2k, we are writing 2k common over here, and the term over here that will be mod of a. Next result we have, it is combination of all these results that we have studied over here. So we are saying that log a raised to the power alpha x raised to the power beta, that will be equal to beta log a raised to the power alpha x. This is equal to beta by alpha log base a x. So this is the result we have over here. This is the result we have over here, and we have x is greater than 0, a is greater than 0, a is not equal to 1, and alpha is not equal to 1. The next result we have already seen. Now the next result we have, it is, we are talking about this result, it is a raised to the power log a to the base b. The answer we will have, this is equal to square root of a if we are saying b is equal to a square. So how we are solving this value? In place of b, if we substitute a raised to the power 2, we get it is log a square a. This is equal to 1 by 2. The value we will have it is a raised to the power 1 by 2 log a to the base a, and the value of log a to the base a, it is equal to 1. So we get it is equal to square root of a. Next we have a raised to the power log b to the power a. We are saying this will be equal to, if we substitute b is equal to square root of a. If we substitute b is equal to square root of a, we will have a raised to the power log base, we have it is square root a, and the value we have over it a. This is equal to a raised to the power square root a, means we are talking about it is log a raised to the power 1 by 2a base. So it is a raised to the power 2 log base a and a. This value it is 1. So we are saying the answer is equal to a square. So in this case, the answer we have it is a square. The conditions are same in both the cases, that a is greater than 0, b is greater than 0, and b is not equal to 1. Next we have certain problems based upon these properties we have studied. First is, we have to solve this equation. It is 3 into x raised to the power log 2 to the base 5 plus 2 raised to the power log x to the base 5 is equal to 64. So we are saying that this term we are talking about, this term we can write, it is 3 into 2 raised to the power log x base 5 plus 2 raised to the power log x base 5 is equal to 64. So we get it is 2 raised to the power log x base 5 is equal to 64 by 4, that is equal to 16, that is equal to 2 raised to the power 4. So we obtain that log x to the base 5 is equal to 4. So this implies us that x is equal to 5 raised to the power 4, that is equal to 625. Next is 4 raised to the power log 16 4 plus 9 raised to the power log 9 3, that is equal to 10 raised to the power log x 83. Now look at this first term over here. We can write it in the form 4 raised to the power log 4 square. 4 square means 1 by 2 will come over here, and this is the term 4 we have, plus 9 log, we are writing 9, and over here we are writing it is 9. So basically we will have the power 1 by 2. So this term we will obtain 2 over here, and this is equal to 10 raised to the power log of x 83. Now the value of this term log 4 to the base 4, it is equal to 1, log 9 to the base 9 is equal to 1. So square root of 4 is 2 and square of 9 is 81, and we obtain this is equal to 10 raised to the power log x 83. This value is equal to 83. So if we take log over here, we get it is log base 1083, that is equal to log base x 83. Now comparing both these values, we obtain that the value of x we have, that is equal to 10. So we are saying the value of x we have, it is equal to 10. Next is prove that a raised to the power square root of log b to the base a minus b raised to the power square root of log b to the power log a to the base, this time it is log a to the base b, this is equal to 0. Now the formula for change of base we have, it is log of m to the base b, that is equal to log of m to the base a divided by log of b to the base a. So if we start with this term, we are saying it is a raised to the power square root of log of ab, and we want to change the base over here. We are saying it is log of ab, and I want to change the base to b. So I will get it is over log of b a. So this gives us that log a b into log a to the base b, that is equal to 1. So we are considering that we have into 1 over here, and in place of this 1 we are substituting this value. So we get it is a into square root of log ab into square root of log ba into square root of log a b. Now look at these two terms. The product of these two terms will give us a raised to the power log ab into square root of log of ba, and this is equal to, now the result we have is that a raised to the power log x to the base a, that is equal to x. So if we look at this term over here, it is a raised to the power log ab whole raised to the power square root of log a b. The value of this term, we are saying this will be equal to b. This a is there, this base is a, so this value is b, and it is raised to the power square root of log a to the base b. Now look at, substitute this value in this equation. We are saying if we subtract both these values, these are equal. What we obtain is that the value of a raised to the power square root of log b to the base a, that is equal to this. So if we subtract both these values, the answer we obtain, it is equal to 0. Next is we have to prove that log of 24, it is log of 24 to the base 2 over log of 2 to the base 96 minus log of 192 to the base 2 divided by log of 2 to the base 12, this is equal to 3. So if we consider the right hand side over here, we consider this right hand side over here, we get this value is, we are having the values in the form. Now over here again we are using the result that log ab into log ba, that is equal to 1. So when we are looking at this value over here, we are having log 96, it is 2 over here and base is 96, that is equal to 1 by log 96 base 2. So this expression, this will transform to log 24 to the base 2 into log 96 to the base 2 minus log 192 to the base 2 into log 12 to the base 2. Now all these terms we can see, this 24, it is a multiple of 12, it is 2 into 12. This 96, it is a multiple of 12, it is 2 into 8 into 12, and 192 is also a multiple of 12 and it is 16 into 12. So we can write from this term, we are saying it is log base 2 into 2 plus log of 12 to the base 2. Next term we are writing it is into log base 2 8 plus log of 12 to the base 2, then it is minus log base 2 16 plus log of 12 to the base 2, and last term we will have it is into log of 12 to the base 2. The value of this term it is 1. The value of this term 8 we can write it is 2 raised to the power 3. 16 we can write it is 2 raised to the power 4. So the value of this term will be 3 and the value of this term will be 4. So we are having 1 plus log 12 to the base 2 into 3 plus log 12 to the base 2 minus 4 plus log 12 to the base 2 into log 12 to the base 2. Now if we multiply these terms, the answer we obtain, it is 3 plus 3 log 12 to the base 2, then plus log 12 to the base 2 plus log 12 to the base 2 whole square. The next terms we will have, it is minus 4 log 12 to the base 2 minus log 12 to the base 2 whole square. So these two terms, these get cancelled and the value we are getting over here, it is 4 times log 2 to the base log 12 to the base 2. So we are saying these two values, these also get cancelled. So the answer we are left with is 3. This value we are saying the answer we are left over here, it is 3. Next is solve for a and lambda. If it is given that log of a to the base lambda into log of lambda to the base 5 into log of 25 to the base lambda, this is equal to 2. So if we look at these two terms, we can write it is log lambda to the base 5 into 25, we can write it is 5 square. 2 comes out, it is log of 5 to the base lambda, and the value of this term, this is equal to 1. So the whole term we obtain, the value of this term, it is equal to 1. So the answer we obtain over here, it is 2. So we are saying what we are left with is 2 times log of a lambda is equal to 2. This implies log of a lambda is equal to 1. So this implies us that lambda is equal to a. This implies us lambda is equal to a. Next is properties of monotonicity of logarithm. So first we are talking about it is the case when we have constant base. So if it is being given that log of x to the base a is greater than log of y to the base a, we are talking about the case when the base over here in both these cases it is a. So we are saying that this is equivalent to this system, it is equivalent to the system x is greater than y is greater than 0 if a is greater than 1 and it is 0 is less than x is less than y if a belongs to the interval 0 to 1. So what we can say from this is that whenever the base are same, then this sign will remain same. We are talking about x will be greater than y is greater than 0 when a is greater than 1, and this sign will reverse, if we have a belonging to the interval 0 to 1. So you must remember these kind of conditions because these will be directly used when we will be solving the problems related to inequalities. Next is log x to the base a is less than log y to the base a. This implies us 0 is less than x is less than y. Again, look at this sign over here, it is less than, the sign over here between x and y, it is x is less than y and x is greater than 0. If we have a is greater than 1 and if a is less than 1, then we have x is greater than y is greater than 0. Next is log x to the base a is greater than p. We are talking about the condition. If we are saying log x to the base a is equal to p, then what this thing implies us is that a raised to the power p is equal to x. So we are talking about two conditions over here. We are saying when a belongs to the interval 0 to 1, and second we are saying when a is greater than 1. Now clearly we have that for both these intervals, for both these regions, for both these values of a, the behavior of this function will be very different. So this thing we can see over here. We are saying that log x to the base a is greater than p. This is implies and implied by x is greater than a raised to the power p if the value of a is greater than 1, and 0 is less than x is less than a raised to the power p if 0 is less than a is less than 1. Similarly, this last result we have, it is log of x to the base a is less than p. This is for these two cases. So you must remember these inequalities, that how the log function is behaving when the bases are same on both the sides. We have the constant. Next case we are discussing over here, it is the variable base. So the first condition we are saying is that log a to the base x is defined if a is greater than 0, x is greater than 0, and x is not equal to 1. So we are saying if a is greater than 1, then log a to the base x, we are saying this x, we are saying this is variable base. So this is monotonically decreasing in the interval 0 to 1 union 1 to infinity, and if 0 is less than a is less than 1 in the interval, means we are talking about the values of x. If we have the value of a lying between 0 and 1, then the function log a x, this is monotonically increasing in the interval 0, 1 union 1, infinity. So we have listed certain properties over here. First is, we are saying a is greater than 1 and p is greater than 1, then we have log p to the base a, this is greater than 0. Next is, if we are saying that the value of a lies between 0 and 1 and p is greater than 1, then we will have the value of p base a, it will be less than 0. Next case we are talking over here, it is this next case we are saying, it is if a is greater than 1 and the value of p lies between 0 and 1, then we have log p to the base a, it is less than 0, and if we have p is greater than a is greater than 1, then we have the value log p to the base a, it is greater than 1. So if we look at this result over here, we are basically saying that p is greater than a and the value of p is greater than 1 and the value of a is greater than 1. So if we are talking about the value log base a p, that will be greater than log base a, and this value that is equal to 1. So we are getting the result in the form that log p to the base a is greater than 1. Next we are saying, the next we have, it is if a is greater than p is greater than 1, then 0 is less than log p to the base a is less than 1. Now the condition that is different over here, it is in the previous case we are saying P is greater than A. Now in this case we are saying A is greater than P. Then we have the value of log, in this case we were having log P to the base A is greater than 1, and in this case we are having log P to the base A, it is less than 1. Next is if 0 is less than A is less than P is less than 1, then we have 0 is less than log P to the base A is less than 1, and if 0 is less than P is less than A is less than 1, then we have log P to the base A is greater than 1. These are the last two results that are mentioned over here. So in place of just cramming these results, you must practice the as many problems as you can based upon these results. Then you will get used to these results, that how to use these results. You will come to know how to use these results. So next topic we have, it is graphs of logarithmic function. So the first graph we have, it is for the function y is equal to log x to the base a, and the condition we have over here, it is that a is greater than 1 and x is greater than 0. And the second graph we are talking, it is y is equal to log x to the base a, but the condition over here it is different. We are saying that the value of a, it is varying from, in this case it is greater than 1, and in this case it is varying from 0 to 1, and we know that in this region when the value of a is greater than 1, it is monotonically increasing. So the graph we have, it is in this form. And when we are talking about the values when a lies between 0 and 1, the graph, it is monotonically decreasing. Graph of the function, it is monotonically decreasing. Next is if the number x and the base a are on the same side of unity. On the same side of unity means either condition we have is x is less than a, x is less than 1, a is less than 1, or we have the condition x is greater than 1 and a is greater than 1, then we are saying that the logarithm is positive, and the graph we have, it is in this form. So we will have the graph, we are talking about the case when a is greater than 1, the graph will be of this form, and when a is less than 1, the graph will be of this form. The only difference is now we are not having the negative values over here. Next is if the number x and the base a are on the opposite side of unity. If they are on the opposite side of unity, then the graph of logarithm, it is negative. We are seeing the graph of the logarithm, it is negative. So we are talking about the case when x is greater than 1 and a is less than 1. Second is x is less than 1 and a is greater than 1. So this is the graph for this, and when a is greater than 1, this is the graph for this logarithmic function. Next is the graph of the function y is equal to log of mod of x. We know that when we are plotting the graph for the function y is equal to f of mod x, it means we are talking about the image we have to take along the image along y axis. So the graph of log x when a is greater than 1, it is in this form, and the image of this line along y axis, it is this. Similarly, when we have the value of a lying between 0 and 1, this is the graph of log x, and the image of this is this. So these are the graphs of y is equal to log mod x to the base a for the two cases when a is greater than 1 and when a lies between 0 and 1. Next is graph of y is equal to mod of log of mod of x to the base a. Now the graph of the function y is equal to, we are talking about the function y is equal to log of mod x to the base a. We have already seen that it is of the form, we will have the graph in this way and we will have the graph over here in this way, and in this second case we have the graphs in this form. Now when we are plotting the graph for, if we are taking the modulus over here, we are talking about the mod of this value, we are saying we will have to take the image about x-axis, the lower portion of the image of this lower portion. So the image of this portion, we are saying the image of, I am marking it with this red portion in this first case, the image is this, and image of this portion we have it is this, and we have to remove this portion of the graph from this figure, and hence we are obtaining, this is the graph for y is equal to mod of log of mod x to the base a, and the condition where here we have it is a is greater than 1. Similarly, for this portion we are saying this is the image, and for this portion this is the image. Next step we have to do is, we are ignoring these two portions. So we have the graph of this function, this is the graph of this function when 0 is less than a is less than 1. Next is the graph of y, mod y is equal to log a mod x. Now in this case we are saying it is mod y over here and mod x over here. So this is the graph for the case when a belongs to the interval 0 to infinity minus the point 1, we are saying a cannot be equal to 1. Now the graph of this function, it will be of the form, it is the combination of all these graphs we have studied previously. This is the combination of all these graphs. So this is the required graph for mod of y is equal to log of mod of x. For more details related to these kind of graphs, you can refer to the video related to the graphs that we have studied in the chapter trigonometric functions. For these kind of graphs, you can see the details over there, that how we can plot the function mod y is equal to fx, how we can plot the function y is equal to f of mod x. So all these things, these are explained in detail in these videos. So you can refer to these videos for the details of these graphs. Next is graph of y is equal to log of, this is greatest integer of x, this is greatest integer function, and the base given is a. So if we calculate the values over here, we are saying when 1 is less than equal to x is less than equal to 2, the value of greatest integer of x, that will be equal to 1. So this implies us that the value of log to the base a x will be equal to 0. Next we are saying when 2 is less than equal to x is less than 3, this is not equal to, it is less than 3. Then we have greatest integer of x is equal to 2. This implies us log a greatest integer of x is equal to log 2 to the base a. So we are saying for the region 1 to 2, we are saying for the region 1 to 2 the answer we have it is 0. For the region 2 to 3, we are saying the answer we have it is equal to log 2 to the base a. For the next region we are saying the answer we have it is log 3 to the base a. We will have greatest integer of x is equal to 3. So this implies us log x to the base a, that is equal to log 3 to the base a. We are talking about 3 is less than equal to x is less than 4. So this is the required graph of the function y is equal to log of greatest integer of x to the base a. Now the next question we have is to arrange these numbers. We are saying log 2 to log x to the base 2, log x to the base 3, log x to the base e and log x to the base 10. We have arranged these numbers for these two cases. First is for x is greater than 1. So we are saying that if we look at these numbers, we have 2 is less than, e is less than, 3 is less than 10. So when we are talking about the case when x is greater than 1, then we have this case. From this result we can write log 2 to the base x is less than log e to the base x is less than log 3 to the base x is less than log 10 to the base x. Now this term we can write, this term we are saying we can write it is 1 over log x to the base 2 is less than log 1 over log x to the base e is less than 1 over log x to the base 3 is less than 1 over log x to the base 10. So this gives us that log x to the base 2 is greater than log x to the base e is greater than log x to the base 3 is greater than log x to the base 10, because we know that the log function, it is monotonic when monotonically increasing when x is greater than 1. So this is we have obtained. In the second case, when we are saying that 0 is less than x is less than 1, we know that the log function, it is monotonically decreasing. So this sign of inequality, it will reverse in this case. This sign of inequality will reverse in this case, and this sign of inequality will reverse in this case. So we are saying that this is the ascending order, and in this case this is the ascending order. So it depends upon the value of x. We are saying the region in which it will be monotonically increasing or decreasing. Next is, if log of 11 is equal to 1.0414, we have to prove that 10 raised to the power 11 is greater than equal to 11 raised to the power 10. So if we look at this value, we are talking about log of 10 raised to the power 11, that is equal to 11 log 10, that is equal to 11, and log of 11 raised to the power 10, that is equal to 10 log 11. The answer we obtain, it is 10.414. So clearly what we get is that 11 is greater than 10.414, and the base we are saying over here, the base we are talking about, we are writing it is log base 10 raised to the power 11. We are saying it is greater than log base 10 11 raised to the power 10. We have just substituted these values over here, that for 11 we have substituted this value, and for this we have substituted this value, and for the base 10 we know that the log function, it is monotonically increasing. So this implies us that 10 raised to the power 11 is greater than 11 raised to the power 10. Next is, find, if this condition is given to us, it is log to the base 2 x minus 2 is less than log to the base 4 x minus 2. We have to find the interval in which x lies. So here we are saying that x minus 2 is greater than 0. This is the first condition we have. So it means that we are talking about the case that x is greater than 2. So from this question we are writing this term, we are saying we can write it in the form log x minus 2 to the base 2, it is less than this 4, we can write it is 2 raised to the power 2. So it is 1 by 2 log base 2 x minus 2. Now the next question we have is, we have to prove this result, that log of n plus 1 to the base n is greater than log of n plus 2 to the base n plus 1, where n is given to be greater than 1. So, to prove this result, we are using this result over here. We are saying it is n plus 1 over n. We can see it is equal to 1 plus 1 by n. This is greater than 1 plus 1 by n plus 1, and this is equal to n plus 2 divided by n plus 1. Now we are talking about the case when n is greater than 1. So for n is greater than 1, we have the log is increasing function. So what we get from this is, we are saying we obtain that log to the base n, n plus 1 over n, we are talking about this value, it is greater than log of n plus 1, n plus 1 by n. We are saying in these two terms, it is the base n over here and it is the base n plus 1 over here. The base has increased. So we are saying that this value is greater than this value. Now look at this term over here. We are saying that n plus 1 is greater than n plus 2 over n plus 1. So we are saying that this is greater than log of n plus 2 over n plus 1, and the base we are using over here, it is n plus 1. So we obtain that log of n, this term if we talk about, this term we are saying it is log of n, it is n plus 1 minus log n, and this is greater than log of base is n plus 1, in this case the base is n, and then it is n plus 2 minus log of n plus 1, base is there and n plus 1 term is there. Now look at these values over here, log n to the base n, it is 1, and this value is also 1. So both these values we are saying these gets cancelled, this 1 and 1 gets cancelled. So what we are left over here is that log of n plus 1 to the base n, this is greater than log of n plus 2 to the base n plus 1. We are left with this term, and this is the result that we have to prove. This is the required result that we have to prove. Next we have is how to find the maximum value of, we are talking about lambda 1 log x to the base a plus lambda 2 log a to the base x. If we have some number in this form or expression in this form and we want to calculate the maximum value over here, these conditions are given that the value of a is greater than 0, x is greater than 0, a and x they cannot be equal to 1, and lambda 1, lambda 2 these are positive real numbers. Then to find the maximum value over here, we are using the arithmetic geometric inequality. So we are saying that arithmetic mean is greater than equal to geometric mean. So this implies us that lambda 1 log x plus lambda 2 log x a divided by 2 is greater than equal to square root of lambda 1 log x to the base a into lambda 2 log x to a to the base x. Now look at these two terms over here, it is log x to the base a log a to the base x. So the product of these two terms, will be, the product will be equal to 1. So we are saying that the value of lambda 1 log x to the base a plus lambda 2 log a to the base x, we are talking about this numerator part over here, it is greater than equal to 2 times the square root of lambda 1 lambda 2. So we are saying that the minimum value of this term it is 2 times lambda 1 lambda 2. So based upon this question is given over here, that we have this expression is given and we have to find the least value of this expression. So if we look at these values over here, it is 2 log x to the base 10 minus log 0.01 to the base x. So we can write this is equal to 2 log x to the base 10, and the next value we are saying it is, this term we are saying it is 10 raised to the power minus 2. So this becomes plus minus 2, it comes over here, 2 times log of x 10. So this is equal to 2 times log of x 10 base 10 plus log of 10 base x, and the maximum value of this term, will be, we are using now this result, the maximum value of this is 2 times square root of lambda 1 lambda 2. Lambda 1 is 1 over here, lambda 2 is 1 over here, so we are getting it is square root of 2 into, we are saying 2 into square root of 1 into 1, so answer we obtain it is 4. So we are saying that the least value of this expression it is 4. In this next question we have, which is smaller, it is 2 or log pi 2 plus log pi to the base 2. So if we look at this expression over here, we are talking about this expression, and we try to calculate the minimum value of this expression, clearly we have the least value, we are saying log pi 2 plus log pi to the base 2, it will be greater than 2. We are using this result, it is 2 times square root of lambda 1 lambda 2, and the value of lambda 1 and lambda 2 in this case it is equal to 1. So we obtain that log 2 to the base pi plus log pi to the base 2 is greater than 2. So we are saying that the smaller number will be 2. 2 is the smaller number in this case.